I mean, theoretically, this was talking a little bit of words, but sometimes we don't have to go there. So where are we going to start this? What are we being asked to solve for? Being asked to solve for our KEQ, our equilibrium constant. How do we calculate an equilibrium constant? What is our equilibrium constant expression? Products over reactants. So what are the products in this case? Over our reactants. What are our reactants? Oops. Cl2 and CO. Since our balanced chemical equation only uses one coefficient, the exponents in each of our expressions are going to be 1. So now it's just a question of plugging in the correct numbers. Okay, so we've got a whole lot of numbers up in the question, and that becomes kind of one of the things that we can try and piece together. So if we look through this, we really only need 3 numbers. But we need the 3 numbers that correspond to what? Concentrations of these species at any point in time? No, and very specifically must be equilibrium. Okay, and when I said no, I was answering me no, you were right.
Oh,
okay. We need our equilibrium concentration. So now that's the question of going back to our question and reading through it and trying to figure it out. Okay, this last phrase part is what sets us up. We get 0.08 molar COCl2, 0.02 molar Cl2, and 0.02 molar carbon monoxide at equilibrium. Those are now the values that we would need to plug into our system. All right, so all we've got to do is now plug and chug. COCl2 was our 0.08. Our Cl2 was 0.02. And our CO was 0.02. Now what do we go through and do? Enter it in the calculator and we get our magic number. What's our magic number? 200. What does that mean? Okay. To help with that meaning, I would go back to what our KQ expression was. Okay? When we talked about it, I believe someone actually mouthed out what the general form of the statement was. Our general form is the concentration of products over the concentration of reactants. Okay? If our value is equal to 200, what does that mean? Well, it means the ratio of products to reactants is a very large number. What does that mean? I have more products than I have reactants. So when I'm running this reaction, it is favorable in formation of our products. Okay? It would be a spontaneous reaction. Okay? Before we continue on real quickly, everybody got the sign-in sheet? Nope. Okay. Oh. I'll come back to you in a second. There was one more note, I think. Another question came up. Why are we giving all these numbers? What you will probably start seeing, if you haven't seen already, is you might see the formation of ice tables. Ice tables are a way for you to structure the information given to you so that you can potentially organize and figure out what information you need to use versus not use. Usually when we structure an ice table at the very top, we run our chemical expression, and then we do our ice, I, for initial. What are the initial concentration of Cl2? 0.1. What's the initial concentration of our carbon monoxide? 0.1. What's our initial concentration of our COCl2? 0. So So there's our I. We have a C next. What's the C stand for? Change. Okay. If we're going to run this reaction, what's going to happen at this point? What do you think would happen to the reactants? They should go down. So those should be negative, and our product should be positive. How much is it going down by? Okay. It's going to go down by some factor that's related back to the equilibrium. Okay. So I don't know what that is necessarily yet. So I can leave those all as x's. Okay. And technically I would leave them all as 1 times x. Why 1 times x? If chlorine goes down by 1 mole, what should the carbon monoxide go down by? 1 mole. How'd you come up with that?
X, they're the same value, so it's going to be the same across all.
It's technically 1. Why am I putting the 1 in there? Why is it the same value?
It's the constant in front of, it's like the n value.
It's our coefficient in front of each of our materials. Because the coefficient in front of all those materials is 1, I'm using a 1 in all of those. That's why the x is the same x. Okay? The last thing on our ice table would be, how do you spell ice? E for equilibrium. Okay? Within that equilibrium, what do we see? Let's just start with the very first value. What do we get? As we read the question. If we combine these things, we get 0.08 what? Molar of COCl2. Okay? There are a bunch of other values given. Oops, accidentally we forgot to give them. Can you solve this? Can you tell me what K is still? Yeah? How come? I don't know my equilibrium concentrations for chlorine or carbon monoxide. How can I possibly solve for the equilibrium if I don't have those values?
You can find x.
We can go back to our expression. Our ice table can help us out with this. Okay? How did I get 0.08? I started with 0. What had to happen? I had to add 0.08, which means x was 0.08. What does that mean negative x is? Negative 0.08. What's 0.1 minus 0.08? 0.02. What was the value that was given that I happened to erase? 0.02. Okay? So there's different ways we can organize the logic of our system to help us calculate and determine what those values were. So if we weren't explicitly given those values, we could calculate them from some of that given information. Once we know our equilibrium concentrations, we can then sub into our equilibrium expression. Which means to solve these, we need to know what our equilibrium expression is, and then we need to know what those equilibrium concentrations are so that we can start making these subs. Kind of, sort of? Okay. Ice tables become notoriously painful to deal with. Okay. I've not seen a whole lot of them in the slides. I don't know how much you're going to end up having to use them or not. Okay. We'll just kind of see as we go. Make sense? I would bet Alex is going to have you use ice tables right and left. Okay. When we consider our reactions, okay, this is why we never get 100% yield. What does that even mean? What about this tells us that we didn't get 100% yield?
There's still some reactants left.
There's still some reactants left. Why are there reactants left? What happened?
Not enough energy.
I can add tons of energy. I'm still going to have reactants left. The equilibrium. And in specific terms, all reactions are reversible. They will always backflow to reactants. Okay? So this is one of the reasons that contributes to why we never get 100% yield, because we're always going to get some backtracking towards our reactants. Okay? How much becomes a different argument, okay? And that's an argument for a different day. Okay? So if we're looking at our equilibrium constant, it is something that has to be determined experimentally. We would determine our concentrations at equilibrium. We'd go through, we'd run our calculations. So we've got two chemical reactions shown up here. Hydrogen gas reacting with carbon monoxide to form methanol. Okay, it has a KEQ of 1.3 times 10 to the 7th. HCl decomposing into hydrogen gas and Cl and chlorine gas gets us an equilibrium constant of 4 times 10 to the negative 5th. Okay, our blue box, what does the value of the equilibrium constant tell us about the relative amounts of reactants and products? You've got two reactions here. Look at those values and discuss what that means about the reactants and products. So let's talk through it. One thing I would immediately try and get you to think about and trigger with is stop looking at the big numbers. Okay? We're seeing powers of 10. How good are people at manipulating powers of 10? On the whole, people suck at it. Okay? Pretty universally. Okay? This is why, have you heard about acids and bases? When we talk about acids and bases, do we talk about them based off the concentration of acid present? Typically, we reference them as pH. What is pH? You'll learn about it later in this semester. It's the negative log of your concentration. What? Why do you do that? Because it converts the concentration from this wicked power of 10 to a number between 0 and 14. Humans can deal with the number 0 and 14 relatively well. I would argue we struggle anything beyond 10. Okay? But that converts that number, that power of 10, into something that's more manageable to work with. Okay? So what I would argue we could go through and do first is make sure that we understand what our K is referencing. What does K reference? What does K reference? Our products over our reactants. That becomes critical to this conversation. If we look at the first number, times 10 to the 7th, is this a really big number or a really small number?
Big.
It's a really big number. So for it to be really big, which of these terms is bigger, products or reactants? The products have to be bigger. So if I see a large K value, that means I get lots of products. That means the forward reaction is spontaneous. What happens if I move to the other one, 10 to the negative 5th? Is that a big number or a small number?
Small.
That's a small number. Okay? Because it is a small number, what does that tell me about the products to the reactants?
More reactant.
I have more reactants than I have products, which is why I get that smaller numerical value. I can use those chemical equations to help me out. Okay? Before we move on to the summary slide on this, can I have a negative KEQ? Because a negative value is smaller than both of those, right? Can I get a negative KEQ?
No,
Why not?
can't have a negative amount of products or reactants.
We're talking about the concentration, the actual concentration of your products and your reactants. You can't get a negative value there, which means when we're talking about our KEQs, they will always be positive. So when we're talking big and small relative to what? (10 to the negative 5th) relative to 0 is still really big. Relative to 1. So when we're discussing big and small, 1 is our 0 point for K. A number larger than 1 means I have more products than I have reactants. A number smaller than 1 means I have more reactants than I have products. Okay? So if I shift focus away from these wicked, weird-looking numbers and consider where they are relative to 1, that can help me predict these product and reactant systems. Whoops. Okay, which gets us to our summary slide. It's now relative to 1. If KEQ is larger than 1, the products must be larger than the reactants. If the KEQ is less than 1, the reactants must be larger than our products. Where'd the sign-in sheet go there? Okay. This can help us understand an extent of the reaction. I think you got that right. Okay. A larger K means the reaction happens to a greater extent. More product is formed. Okay. If we think through general chemistry stuff, would we expect or want reactions to produce more products? Is that a good thing or a bad thing? It's a good thing. Do I want to produce more carbon dioxide? Is that a good thing to produce more carbon dioxide? Okay. So when we're talking about the extent of our reactions, good and bad is kind of a secondary concept. It depends on what chemical reaction you're trying to run. If we're trying to make something, we want to make it, so I want lots of products. If I'm concerned that that product of that chemical reaction is a toxin, I don't want to make it. I'm going to shift focus on how I would look at that reaction. Kind of make sense? Which sets us up with this slide, which is giving me a little bit of heartburn and panic. Okay. If K equals 3, and we start with 1 molar A and 0 molar B, draw a graph that shows how the concentrations of A and B change over time as the reaction reaches equilibrium. Okay. So to start off with, okay, our molarity is on the left. If I was going to draw A, where should I start A? The top of this line or the bottom of it? I started up at the top. So that's where my A should start. Where should B start? Should start at the bottom because I don't have any B. What's going to happen initially? What happens when I say reaction go? The A concentration should drop because I'm starting to convert A into B. What should happen to the B concentration? It should increase. Okay. Now the question becomes, where do they balance out? Okay. Blue box, it's time for a conversation. Talk at your tables, try and figure it out. All we've really addressed is our starting point. Now we need to address where the ending point is. The lines we now have on this curve are incorrect. Why are they incorrect? So this isn't just I'm going to draw lines. Your lines have to take into consideration that K value. So a little bit sloppy, really sloppy. Okay, in the blue, our addition there. Our K expression is 3 equals our products over reactants. Okay, so trying to figure out the balance of where these things are, okay, what does that mean? Do I have a value larger or smaller than 1? Larger, which means I have more products than reactants. How much more products do I have than reactants? Well, now what I'm asking to do is to rearrange that equation to quantify the relationship between reactants and products. How can I do that? Let's multiply both sides by the concentration of reactant. On the right-hand side, what happens with my reactants? They cancel, right? What happens on the left-hand side? I get 3 times the concentration of my reactants equals product. So at equilibrium, if I said this was my reactant concentration, so here we are, a flat line. That flat line is my equilibrium. It's no longer changing concentration. Where should my product concentration be? What did the math say? 3 times higher. So that's 1, so 1, 2, so maybe there, I don't know. Okay. Again, I'm not doing a very good job with my flatlining, so we'll kind of force it. Okay. We got one more. No, you're okay. Okay. Oh, okay. There's one more piece of information we should watch out for within this. If I look at where I've drawn this line, what does that line up with? That lines up with the exact concentration of my reactant to begin with. Does that make physical sense? Did all of my products get formed? All of my reactant become product? No. So that cap is now problematic. So we looked at the reactant and said, oh, the product needs to be 3 times as high. But when we did the 3 times as high, that put our product concentration at the reactant concentration. Back to the money exchanging. You can't make more money from our demonstration. Okay? So I need my product concentration to be 3 times as high as my reactant, but at the same time, the total of those two can't be higher than 1. So what does that mean? Whoops. My product concentration should come in at 0.25. So that's not my product. My reactant should come in at 0.25, and my product should be 0.75. So did I draw it to scale? No, not remotely at all. But if I can add those numbers to quantify it, okay, I can hopefully sidestep someone looking at it and being like, you did a horrible job drawing, by saying, but these are my numbers. It's a logarithmic scale. No, it's not, but make sense? What you're trying to do is piece all of that information together into a graph. Okay? I'm going to not record this part of this.
So I know that your initial concentration went down to 0.25, and then the concentration of B went up to 0.75. That'd be a 3-to-1 ratio between A and B.
So cool. And I love how you phrase that. That's a phenomenal phrase. Is K a ratio? Yeah, exactly. That's right on the nose. Yes, K is a ratio. It is the ratio of our products to reactants. That is exactly what it is. Okay? And I deleted everything, of course, but that's what I had to do. Kind of, sort of. Okay? We can look at this kind of pictorially. Okay? Our first line, the first thing that's being shown on top of this, okay, is typically how we would think a reaction progresses. We start with all reactants and then we end with all products. Okay? That's kind of how we discuss through every other aspect of chemistry our chemical reactions. And not every aspect, how we discuss fundamental chemistry and how we do Gen Chem 1. We say, oh, it just goes to products. Yep. But we never quantified how much it went to products. Why did we not quantify it when we talked about it at 151? Because that's 152 content. And that's where we have to add that extra layer that we have reversibility behind the reactions, and we never actually go all the way. Okay? The all the way has to do with the magnitude of that K value. The larger the K value, the more it gets to, or more it approaches, 100% conversion. But we're never there formally. Excuse me. Kind of make sense? Okay. This is one that I actually spent a little time in the tutoring center because no one was talking to me. I looked at this expression here, the delta G equals negative RT ln KEQ, and I was like, that looks really familiar. Right? And that one might not look really familiar immediately, but if we go through and look at the bottom one, KEQ equals E to the negative delta G over RT. Does that look familiar to anybody? Yeah? What does that look like? That looks like the Arrhenius expression. Right? But the Arrhenius expression, when we looked at an individual reaction, was just talking about that. That has nothing to do with delta G. Okay? What is delta G and KEQ referencing? It's in the name, KEQ. Equilibrium. What's equilibrium? That's an important one. We should know what equilibrium is. What is the equilibrium? Yeah, it's the ratio of our products to reactants. When? When is it the ratio? What's equilibrium? When is equilibrium established?
When the forward and reverse reactions are the same.
When the forward and the reverse reactions are the same, you're missing a word.
They react at the same rate.
The rate of the forward and the reverse are the same. So if I'm looking at an activation energy, I'm referencing that R value. Okay, that would be for my forward reaction. If I'm going to bring in delta G, I'm talking about equilibrium. And at equilibrium, what am I also going to bring in? The activation energy for the reverse. And if I look at the difference between the activation energy for the forward and the reverse, what do I end up with? What's that black space? The difference between those two values. Do better. It's the delta G. So I can go through and I can solve my Arrhenius expression, set those equal to each other, and do a bunch of algebra manipulations, and I get those expressions. That's pretty wicked. Do you want to do all that? No? Okay, what should you do? You should probably write these equations down because you'll need to use them because you don't want to derive them. Okay? Do you have a cheat sheet? Are you writing stuff on that cheat sheet? Like, say, an important expression that would allow you to go through and solve delta G relationship to equilibrium constant. Yeah? Yeah, no one seems to be writing things down, so I'm a little freaked out. Okay? That's an important expression that you're going to have to manipulate. Okay? So if we now move to a blue box, calculate the delta G for each reaction at 298 Kelvin. Will each reaction happen spontaneously at this temperature? Okay? So now what we've got to do is a bunch of plug and chug. Fire away. Time to actually solve those out. For that top one, what did we get? Oh God, yeah, just show me.
The top and then bottom.
Okay.
So 4,000.6 kilojoules or
3.
40.6 kilojoules.
Joules, the bottom one. Whoops. Should not have recorded this part of it. Apologies. So hopefully for that top one, you're getting negative 4,583 joules, kind of ignoring sig figs at that point. And for the bottom one, you're getting a positive 25.089 joules. Okay, so we've now calculated the delta G. Did we answer the question? No. What was the question? Or all of the question, we should say. Is it spontaneous or not? How do we decide if it's spontaneous or not? I'm going to come back to that. How do we decide if it's spontaneous or not? The sign. Okay? If it's a negative sign, what does that mean? Spontaneous. If it's a positive sign, what does that mean? Not spontaneous. Okay? This is why I like to specify the signs in front, because answering that question of spontaneity can help me if I've got a sign explicitly identified. Does that make sense? Okay. There was another statement, or a couple statements made. Did I break something? Not yet. Yep, I did. Okay. First statement that I want to go through and address. Okay, we solved it for joules, not kilojoules. Why? What did the question ask us to solve it for? As far as units go.
Didn't specify.
It didn't specify. Because it didn't specify, we could solve for whatever we wanted to. Why did we pick joules? Because we happen to remember 8.314 joules per mole Kelvin, okay, within our system. That makes it easier for us to manipulate and deal with. Okay? If the question specified kilojoules, we'd then have to do a conversion. Okay? Relatively straightforward, simple conversion. Okay? Just shifting our decimal point if you were comfortable with that, or you actually write it all out. Okay? Based off the numbers we have here, which do you think is more important or relevant for us to use, kilojoules or joules? And you could easily say, I don't think there's a difference. That's fine too. Okay? The top one is going to become negative 40.583 kilojoules. The bottom one would be positive 25.089 kilojoules. Why would I choose one over the other? This comes back to the statement we already made at the beginning. How good is the human brain with numbers? Okay? It sucks. So do we want to use a number that is way more than I can count on my fingers, or one that's kind of close? That's the preference on why we're using kilojoules versus joules. The joule value is just such an absurdly large number that I'm choosing to convert it to kilojoules. Is that what you're going to raise your hand for, Emily? Yeah. Hi. Kind of all makes sense? We've got numerics within it. Okay, we've answered all the questions, but then a last statement came out. You didn't have to do a calculation. What do you mean you didn't have to do a calculation? Right out of the gate, I know that top one is spontaneous and the bottom one is non-spontaneous. Why? Look at the size of your K value. Is that K value above 1? Yeah? That's spontaneous. Is the other K value below 1? Yeah? That's not spontaneous. You don't have to run the calculation if you're paying attention to the meaning behind those K values. Right? Did you have to run the calculation this time? Yes. Why? It told you to calculate it. That's why you do it. Okay? But you don't always have to do that. Kind of make sense? Cool. Which then sets us up with a nice little table that can try and summarize this. If we had a K value larger than 1, what did that mean for our delta G? It was negative. If we had a K value smaller than 1, what did that mean? A delta G that was positive. Okay? If it's a negative, what direction does my reaction happen spontaneously? Forward. Okay? At equilibrium, do I have more reactants or products? I have more products. Now we've got a tougher question. We move down to the bottom one. When K is less than 1, what's the reaction direction that happens spontaneously? We're going to get the reverse reaction happening spontaneously. Okay? What does that mean about products versus reactants? I'm going to have more reactants. Kind of, sort of? Yes?
Can you explain why the reverse happens?
So why that reverse happens, if we go back to our energy diagram. Okay, let's look at the delta G being positive. What would our energy diagram look like if our delta G was positive? Here's my reactants. Where do my product energies need to be? My product energy would need to be up here, right? Which is going to happen spontaneously? The ball rolling up the hill to get to my products, or the ball rolling down the hill? That's all it is. Okay? And for those people being, well, what about the hump in the middle?
Yeah.
What about the hump in the middle? When do we discuss the hump in the middle? When do we discuss the hump in the middle? Activation energy. True, that's contributing to it. When do I discuss activation energy? When I care about the speed of the reaction, the kinetics. Are we talking about the speed at which this happens? Nope, which really just means, oops, that's all we're looking at. Our reactants and our products and their relationships to each other. Okay? If the product energy is higher in energy than the reactants, that reverse reaction, I'm going to go from the products to the reactants more easily than I will from the reactants to the products. Kind of, sort of? Good question. Okay. Equilibrium and rate. We actually derived this. Should we go through and do it again? I think it's really neat, but some people don't like it. It's okay. Should we do it again? I can start it so you can get an idea of what I'm talking about. We've got a rate forward and a rate reverse. What would the rate forward look like? Well, it would be the rate equals the rate constant times the concentration of A. What does the rate reverse look like? The rate constant, lowercase k, I'm trying to do a better job about showing those k's now as lowercase versus capital, times, what's the reactant for the reverse reaction? B. If we're at equilibrium, what does that mean? The rate forward equals the rate reverse, which means long equals sign. And because we're mathematicians, or we pretend to be because we're chemists, okay, what we can go through and do is group like terms. The K's are constants, the concentrations are concentrations. So what we're going to go through and do is group the concentrations on one side and group the constants on the other. Okay, and what are we going to end up with? We're going to end up with K over K, and we're going to come back to that one in a second, equals B over A. What was B? As a hint, it's on the left side of our arrows. Right side of our arrows. B is on the right side of our arrows. What was A? What does K over K equal? This becomes dangerous. Is it 1? No, it's not 1 because that's a red K and a blue K, which is very confusing because particularly when you're writing it down, you probably don't have multiple colors. Okay? That red K is the rate constant for the forward reaction. The blue K is the rate constant for the reverse reaction. That's a constant divided by a constant. And a constant divided by a constant is another constant. It could be 1, but it could be any numerical value. And since it's a new constant, instead of showing it as the combination of multiple constants, I invent a new constant. Capital K. What did we just solve for? That's the equilibrium constant. That's the ratio of my products to reactants. That's ultimately being derived from the rates of our reactions. That's kind of neat. Is it easy to get lost in what those K's are? Yeah, it's very easy to get lost in what those K's are. Okay, but before I advance on the next slide, are we okay with this? Can I move on?
So is this a different K from K?
Nope. This is KEQ. 100%. What this is trying to show is where did KEQ come from? Because we pretty much just said KEQ is products over reactants. Why is it products over reactants? Why is that a magic ratio that comes out? That's a magic ratio because of what EQ is. Equilibrium means rate forward equals rate reverse. Okay? Once I know that, I can now sub in those pieces of information and solve for an expression. And that expression that I get is my equilibrium expression. That is my products over reactants. It's one and the same thing. It's where did that ratio come from? Did we just make it up? No, there's a reason behind it. That reason is looking at defining what the equilibrium is. That's the rate of our forward equals the rate of our reverse. Kind of, sort of? Other questions? Yes?
Just more fun one. Why do they use
I swear I looked up the entropy versus enthalpy terms and was like, that was just annoying that the scientists decided to call entropy similar to enthalpy. Though the more I say it's truth, the more I question whether it was actually truth or I just made it up, because I've done that before in the past too. I have no idea what the deal is with K, why that was discovered. I've never bothered to try and look at the history behind why they chose K.
Does it, I mean, rate equations are differential equations in a sense. And if it has like relations to k is used all throughout differential equations. It is like the general constant in differential and like rate equations, so.
That could be why.
Something to do with that.
Yeah, I wouldn't be surprised. Generally speaking, mathematicians come up with mathematics just because they think it's cool to come up with a neat expression. And then somebody comes along and says, oh, that mathematics is actually useful. That explains what's going on here. And then all the mathematicians get pissed and try and do something else. Right? So you get scientists keep coming back and being like, oh, no, that math was useful. Let's play with that. So it is. That's a very likely explanation for it. Okay? But what this is going to introduce is that we do have multiple Ks floating around, and we need to be real careful with their meaning, particularly because, I was going to say because it's all the same unit. It's not the same unit, right? Okay. Our lowercase k was unit 1. Our capital K is unit 2. Okay? Their relationships are very much intertwined, okay, because they sit on the definition of what equilibrium is. The rate forward equals the rate reverse. Okay? So you can pull all of that information out of rates and create these new expressions, but that can become a bit tedious and easy to get confused. Okay? So you need to make sure you keep your K's straight. Okay? So this, I believe, is in Canvas. Okay? I think it is literally called Keeping Up with the K's. Okay. That was the wrong word to use there. So you need to be aware of these things and when you should be using them and when you should not be using them. Some things to point out. When we look at our big K, what are the exponents? Where did the exponents come from? They came straight from the coefficients of your chemical reaction. When we look at our rate, where did our exponent come from? An experimental evidence that we had to solve for. It doesn't come from the chemical reaction. So we have to be real careful because they're similar formats, but they have different rules behind them. So you have to be a little more careful with your manipulations. Make sure you pay attention to that as you navigate these systems. Okay? Particularly as you're trying to retake quiz 1 while you're studying for quiz 2. Right? Okay. We did that. Here's our review for our equilibrium constant, products over reactants. You can also look at Kf over Kb. I used R, she used B. Why did Dr. Schneblin use B? What does B stand for? Backwards as opposed to reverse. Okay? Backwards is probably better because a lowercase r could get confused for an F. Okay? It's the ratio of our products to our reactants when we are at equilibrium. And that becomes an important statement. Okay? If we go back to that chart where we had A decreasing, right? And we did this, and we did our product increasing. Everybody remember that? Okay? If we try and do the ratio at this point in time, is it going to be K? No, it's not constant there. It's still in the process of changing. The only time that our ratio of products to reactants is K is once we've achieved that plateau. At any point after that time, we're now looking at K. Any time before that, not K. It's going to be called Q. But it's not K. Kind of, sort of? Okay. This happens when the rate of our forward reaction equals the rate of our reverse. If a large K or a K is greater than 1, we have more products than reactants. If K is less than 1, we have more reactants than products. This summarizes a lot of that content. How much of that content do you have memorized? Okay, none of it. Ooh, what does that mean? What does that mean?
Practice.
You could do practice. I'm fine with that. That's a good idea. Put it on your note sheet. Okay? Particularly put it on your note sheet as you're doing practice, because maybe what you'll find is you will learn it and you don't need it on your note sheet later on, and you can reuse that space for something else. Make sense? Okay. So, another blue box. Which direction would have a larger rate constant? Forward or reverse? How do you know? So we've got this reaction. Which one do you think would have a larger rate constant? Our KF, she called it reverse. Forward or backwards? However you want to differentiate that. Okay? What do we think? Which has the larger rate constant? Sorry, I talked over you.
The reverse reaction, because since the products are lower, the reverse reaction will require a higher activation energy. And if you look at the rate constant formula, the numerator of the fraction in the formula, activation energy is on top. So a larger activation energy would mean it's a bigger number.
Okay, so where you started to discuss was looking at our energies within our reactions for our forwards versus our reverse. Okay, if we look at our activation energy here, can someone give me the Arrhenius expression? K equals?
K equals A e to the negative EA.
I think that's all I needed. I just needed some piece. Okay. If I end up with a larger EA, so what you've done is looked at our diagram, which is great. I like that. Okay. You've added your labels effectively on this. If I have a larger EA in this, what happens to my K?
It's bigger.
It gets smaller. Okay. That's not an easy thing to piece together. Okay. I would argue where that's going to come in is the negative sign and this E. What I would do is actually straight up take my calculator and I would just say I'm going to pick a big number, e to the negative 1,000. See what my number is. What does the calculator spit out? And then I'm going to go through and do e to a small number, negative 1. Look at the comparison between those numbers to decide how that affected K. Does that make sense? Okay. So dealing with that expression is very kind of dodgy to manipulate. Okay, but that's how I would go through and deal with that so that you can see that system a little bit better. Okay, we could go back to our KF. Okay, so you talked at all the pieces that were important, except unfortunately I think you flipped them all. Okay, if we look at this as KF, and I'll make this over KR for our reverse. If you're saying KR is larger, what happens? What happens to your K value? You get a K value that would be less than 1, which would mean delta G is positive. Here we have a delta G that is negative. Okay? So you found all the proper places to make your interpretations, which is fantastic, but you flipped all the interpretations. Okay? So we got to be real careful with how we navigate these, because in a lot of cases, it's literally a coin toss. Is it bigger or smaller? That's a 50-50. You need to know each of those expressions all the way through. Okay? So let's walk through those pieces again. Going up to the K expression, the capital K expression, I would argue is the most useful here. Okay? Which one needs to be bigger if I'm going to get a large K value? K forward has to be bigger than K backward or K reverse. Okay, so K forward has to be a larger value. Okay, what I would bet you went through and did is you saw this larger value for the reverse and assumed that meant a larger K. It means a smaller K because I'm now getting a lower rate because I have a larger activation barrier. So it's that inverse logic that's happening when you go through and look at the energy diagram. Does that help to make sense?
Could we not just like straight look at the graphical delta G and just not even worry about the activation energy? And
Except, what's the question asking about? So if all you're looking at as the delta G,
yeah, so if we know it's negative, then we know the K is a big number.
K is a big number, true. What are you being asked to solve for? Not K.
Is it forward or reverse?
Which direction has a larger rate constant? If all you're looking at is delta G, do you see a rate constant?
I mean, yeah.
The rate constant has to do with activation barriers. So what you've done is an internal manipulation of how do you relate activation energies to delta G, which is fantastic.
Okay.
But you're taking that a step beyond what we're already looking at.
Okay,
Kind of, sort of.
I guess, yeah.
Where's my stuff? Okay. So we've got our labels up there. We're looking at the K forward being the larger value when we have a delta G that is negative. Okay, and so what we could do is now memorize that. We could say negative delta G means I have a larger K forward. Okay, that's a memorization, not necessarily an explanation of why. Does that make sense? And in this case, it's asking for a how do you know. If the how do you know is I just know the answer, you're not going to get a lot of points on a quiz. Okay. If we're looking at our activation energy diagram, again, or not a diagram, but our number of molecules, our energy, and our activation energy, only the molecules with enough activation energy to react are the ones that are going to progress forwards. Okay. How is that useful? That goes back to dealing with all of the stuff summarized, into two different diagrams. We're now talking about a spontaneous forward and the spontaneous reverse reactions. Okay. These we could also push to exo and endothermic. Okay. We want to kind of dodge exo and endothermic. Why? What are exo and endothermic specifically in reference to? Enthalpy. What are we talking about? Talking about delta G. And delta G is a combination of entropy and enthalpy. So referencing exo and endothermic can get a little bit dodgy when looking at these diagrams, which is why she's not dropping those terms in here. Right? But we're looking at similar systems. They overlap and they match really closely with our enthalpies because what are the units on our enthalpies? Anybody remember? Kilojoules. What are our units on our entropies? Joules. So comparatively, the enthalpy typically dominates our overall picture. Okay. Again, there's gray areas in between. That's the whole point of that 4-quadrant square system that we went through and discussed. But what this is now summarizing is all of those individual pieces. Okay. For a negative delta G, your rate constant for the forward, your forward rate constant is larger. So what she's done is now summarize that again as an answer. Okay? If you're asked to explain it, that's where you have to backtrack where all those systems are coming from. Okay? And in that, there were two possible explanations. You could look at where the equilibrium constant comes from, or you could look at your energy diagram with your activation energies. Make sense? So how would the equilibrium constant change as the temperature increases? Okay, so we've got a big summary of all of our pieces here. Okay, what we want to start doing is now thinking about what happens if you increase your temperature. So start working on this at your tables, and then we'll summarize and end with this. Red box, when are those numbers valid? Red box, when are those numbers valid? $298. Those are our 298 Kelvin values. And this is it changing. So what you're being asked to do is use these values to determine delta G. Once you know delta G, what can you do?
Yeah.
Plug in and solve for K at 298. For the sake of time, because we're kind of there. Seems like an awful lot of calculations, doesn't it? Is there another way? What's our other way? What do you mean, look at the equation? If I have a negative delta H, what value is my temperature always going to be?
Positive.
It's always going to be a positive value, so I can drop that from it, and my entropy will be negative. Okay, so this is negative plus my temperature. What did we just walk through? The quadrants. We just established the quadrants. Remember? Are we spontaneous? When are we spontaneous? So when are we spontaneous here? When the temperature is low. So what do you think is going to happen to K if we increase the temperature? So we can predict something about those numbers of how things are going to navigate, okay, by looking at the size of the numbers, okay, dealing with our delta H's and delta G's. With that, we are definitely done, so I'm going to stop the lecture recording there, and we'll pick up there with the actual numerics Tuesday.